But one of your friend has contacted me for the calculus too.
Yeah, I think Jawaha.
Yes. Thank you so much for that.
Okay.
So example number 3, which is integral from 0 to pi, and the function is sine square x dx. So we again have to apply the trigonometric integrals. And to solve this question, the best way is to apply the identity. The identity is this: sine square x is equals to half 1 minus cos 2x. And there's another identity, which is cos square x half 1 plus cos 2x. Okay, so instead of sine square x, I can write 0 to pi half 1 minus cos 2x dx. Taking half common, so it becomes 0 to pi 1.
Sorry, why didn't you use for like Saturday's example, like I think 1 minus cos x?
You mean this identity, 1 minus cos square x is equals to sine square x?
Yes, why didn't we use this one?
Because sine square x and sine square x and cos square x again are difficult to integrate. So if I write my identity, even if I write my sine square x in terms of 1 minus cos square x, then I have another identity that I have to apply here: 1 minus half plus half cos 2x. So the sine square x and cos square x are difficult to integrate. So we have to simplify them into the functions, into the identities that are easy to integrate. So 1 minus cos 2. Yes.
To eliminate anything that is square.
No, not this. Some functions are difficult to integrate. Like if I write my sine square x in this form, 1 minus cos 2x over 2, I know the integration of cos 2x, which is sine 2x, and again I have to differentiate 2x, which is 2. But sine square x, it's hard to integrate. I have to write in this form sine x, and then sine x again, and that's going to be difficult to integrate. Instead, if I write it in this form, 1 minus cos 2x divided by 2, it's going to be easier for me to integrate it, even if it's sine function or cosine function. Is it clear?
Yes, thank you.
Okay, so half 1 minus 1 dx minus cos 2x dx. Okay, the integral of 1 is x, and the integral of cos 2x is sine 2x over 2, integral from 0 to pi. Okay, now I apply the upper limit minus lower limit. My upper limit is pi minus sine 2 pi over 2, and minus lower limit is 0 minus sine 2 0 over 2. So it's equals to half pi minus sine 2 pi is is 0 divided by 2, minus 0 minus minus becomes plus, and sine 0 is 0. The answer is pi by 2. Is it clear?
Yes.
Okay. And the question that, why I didn't use 1 minus cos square x, because even if I had sine cube x, then it was easier for me to divide sine square x in this form. Okay, like cube in terms of square and sine x, and then I apply 1 minus cos square x, and it becomes sine x. Now I can apply u substitution, like I can say that u is equals to cos x, and then du will become sine x. So I have got everything in the form of u. But here I have only sine square x. I can't, even if I apply the 1 minus cos square x, it's not making my function simpler. It's making my function even more difficult. So the better way is to use the identity instead of solving for sine square x. Is it clear?
Yes.
Okay. Now we have sine square x. Oh, now we are going to move to the example number 4, which is sine 4x. Sine 4x dx. So can I write my function in this form? Sine square x whole square x dx. And I know what is sine square x, which is half 1 minus cos 2x. So I can say this 1 minus half 1 minus cos 2x whole square dx. One by 4 will be outside because it's constant term, inside is left 1 minus cos 2x dx and whole square. Now I have to again apply the a minus b whole square formula. So it will become 1 minus 2 cos 2x plus cos square 2x dx. There is again an identity, that is cos square 2x is equals to 1 plus cos 4x divided by 2. These all identities that we have used earlier, these two identities and this identities are called double angle identities. So it becomes 1 over 4, 1 minus 2 cos 2x plus cos square 2x is 1 plus cos 4x over 2 dx. One over 4, 1, this one and this half will become 3 by 2 minus 2 cos 2x plus cos 4x over 2 dx. Now we have to apply the integral 1 by 4. Integral of 3 by 2 is 3 by 2x minus 2. The integral of cos 2x is sine 2x divided by 2. The integral of cos 4x is cos 4x divided by 4 multiplied with 2. Oh, it's sine 4x. The integral of cos 4x sine 4x. and 1 over 4, 3 by 2x minus 2 cancel out. So it becomes sine 2x plus sine 4x divided by 8. Is this question clear?
Yes.
Okay, even if you want to solve this question, we can solve this question sine square x and sine square x dx. And if I change this sine square x into 1 minus cos square x, and it becomes sine square x again. If I choose u is equals to cos x, then let's see if we can solve this way as well. Then my du is gonna be minus sine x dx. But here we have sine square x. Even if it was sine cube x, then it would have been very easier for me to solve this question. Now I have the derivative of the function, but there is an additional sine x as well, which I can't eliminate it. So there isn't any way to apply this identity, that is 1 minus cos square x and 1 minus cos square x. The only other ways to solve this question is by using the double angle formula. Is it clear? Even if you apply this identity, you will realize after completing 2 or 3 steps, then this is gonna be harder this way. You should apply any double angle identities or other identities to simplify this question.
Is there a technique to follow, like before I solve and waste my time and then realize that this technique worked? Like here, for example, if we saw the sine to the 4, like we immediately solve it like this way. Double angle.
Yes.
Okay.
Yes, there is if I had like odd function, then it would have been easier for me, sine 5x, sine 7x. Then, but if I have a even function, then it's harder for me to apply this formula, because when I substitute sine square x as 1 minus cos square x, and I say that u is cos x, when I derivate it, it becomes sine x dx. But I have here sine square x. I've left up with one sine x additionally. So there is no way to use this formula. The easiest way is to use the double angle identities. Is it clear?
If we had here like sine to the 5, let's say, okay, we will do like sine squared and then squared again, and we will.
If we have sine 5 x
outside,
dx, then we can write our function something like this: sine 4x and sine x dx. Okay, let me just write it down separately and let's solve this question. Okay, so if I have the function sine 5x, I can break it down into sine 4x and sine x. And can I write sine 4x in this form? And instead of sine square x, I can write down 1 minus cos square x sine x dx. Is it clear so far?
Yes.
Okay, now I can say that my u is cos x. Okay, and my du will be minus sine x dx. So my sine x dx will be my minus du, and now applying u in this formula, it will become 1 minus, instead of cos x, I can write u, and here's in a square, so it will become minus u square, and then there's a whole square, and instead of sine x dx, I can say that it's equals to minus du. Taking minus out, taking minus sign out, it becomes 1 minus u square. Okay, and now I can easily apply a minus b whole square formula and can solve it. It will become 1 minus 2u whole square plus u4 du, and the integral of 1 will become u. The integral of u square will become u3 over 3. The integral of u5 will become u5 over 5. There won't be any further integral sign here. Okay, let's sign, and whatever was our u, which was cos x, so I have to write down my answer back in the cos x form. Minus minus becomes plus, cos cube x plus minus cos 5x over 5 plus c. Is it clear? This is the answer. If even if I have odd functions, I can break them down in this form and apply the u substitution easily, and can apply this formula 1 minus cos square x, even if I have the odd function only, power of odd functions. If you have the power of even functions, it's better to apply the double angle identities on the sine x or cos x. Hamda, is it clear to you?
Yes, yes.
Okay. Yes, they have given us some strategies for evaluating. If you have the power of what should be the power of m and what should be the power of n. So okay, if we have two functions like sine x and cos x, and their power is m and n respectively, if the power of cosine is odd, it means m is even, n is odd, then you should apply this identities. If you have sine is, if the power of sine, which is m, is odd, then you should apply sine square x 1 minus cos square x. That's the difference. If both powers of sine and cosine are even, m and n are even, then you should apply double angle identities.
Can we solve a question that contains like both even?
I think we have done this. Let me just check it out. This was even odd. Okay, we haven't done it yet. Okay, let's do it. Hamda, in example number 5, they have chosen both like tan 6x and sec 4x. Both the power are even. I think it's better if we can do the example number 5.
Okay.
Okay. Tan 6x sec 4x dx. Okay, they have said something here that we can use a similar strategy to evaluate the integrals of the form tan mx and sec nx dx. Since d over dx of tan x is sec square x, we can separate a sec square x factor and convert the remaining even power of secant to expression in volume tangent using an identity this. Okay. The way that the derivative of sine x was cos x and the derivative of cos x was sine x, similarly the derivative of tan x is sec square x, and the derivative of sec x is sec x into tan x. And there's another identity which is like the way sine square x plus cos square x was 1. In the similar identities, tan square x plus 1 is equals to sec square x. So instead of writing can I write sec square x, sec 4x in terms of sec square x and sec square x dx? And then my tan 6x becomes,
Why didn't he do like 6 squared x and then also squared again, like before?
in this step, are you talking about?
Yes.
Okay, tan 6x was as it is. I broke down sec 4x in terms of sec square x and sec square x. Base m, the power will be at it.
Yes, I'm saying that why didn't we apply like before 6 squared and then also again squared, not 6 squared, 6 squared? Like secant squared x bracket and then raised to the power.
Okay, you mean like this instead of writing this?
Yes.
Okay. Because when I'm going to apply the identity here, which is sec square x is equals to tan square x plus 1. And there will be a square. If you are saying this, then when I differentiate, when I apply the U substitution, I take my U as tan x, okay, and then my du will be the derivative of tan x is sec square x. There should be a function in terms of sec square x dx. Here, if I choose my sec square x power square, I mean whole square, there isn't any function which is like in terms of sec square x dx. So if I write down sec square x and sec square x, then I have sec square x dx. So instead of sec square x dx, I can write du after applying U substitution. Is it clear?
Yes.
Okay. I think these questions requires a lot of practice. So you will get an idea that which should I do or which should I not do.
Okay. Thank you.
No problem. So it is sec square x. Okay, now if I take my u as tan x, then my du will become sec square x dx. So okay, instead of this, I have to write down tan 6x and sec square x will be equals to 1 plus tan square x and sec square x as it is dx So tan 6x will be equals to 1 plus tan square x as it is, and sec square x dx is equals to du, and my tan x is equals to u. So tan 6x will be equals to u6. 1 plus tan square x will be equals to u raised to the power 2 du. So it will become u6 plus u8 du. When you apply the integration, it will become u7 over 7 and u8 over 8 plus c. And I have to write down my answer in terms of tan x, which is equals to u. So tan 7x over 7 plus tan 8x over 8 plus c. That's the answer. Is it clear? Wait. u9, it will become u9. When I integrate u8, power will be added, so it becomes u9 divided by 9. So that's the answer. Now we have tan 5x and 7 sec 7x. I mean, it means both the power is odd. If power of 10 is odd, if the power of second is odd, is even. Should we solve this question?
I think we solved similar. Both odd.
Yes,
Okay.
both odd.
Yes, okay.
Tan 5 theta and sec 7 theta d theta. So if I write down my answer, if I know that's 1 plus tan square theta is equals to sec square theta, and I can write down my answer in this form: tan 4 theta and tan theta and sec 6 theta and 6 theta d theta. Then it will be tan square theta whole square and tan theta sec 6 theta as it is and sec theta d theta. Then my tan square theta will be sec square theta minus 1. Taking minus that side becomes sec square theta minus 1 is equals to tan square theta. So instead of writing tan square theta, I can write sec square theta minus 1 whole square and then sec 6 theta multiplied with tan theta and sec theta d theta. If I take u as sec theta, then taking its derivative, it will become the derivative of sec theta is sec theta and tan theta. d theta. So instead of writing this, I can write du, and rest is my function is in terms of sec theta. I can replace it with u. So it will become u square minus 1 whole square. Sec 6 theta will be my u6. And instead of this, I can write only du. Applying here a minus b formula, it will become u4 minus 2u square plus 1 u6 du. So it becomes u10 minus 2uh plus u6 du. Now I have to apply the integration here. u11 over 11 minus 2u 9 over 9 plus u7 over 7 plus c, and my u is equals to sec theta. One over 11 sec 11 theta, 2 over 9 sec 9 theta minus sec 7 theta over 7 plus c. Is it clear?
Yes.
Okay. These questions are really easy, like example number 6 and example number 8.
Yeah, I think we already saw similar
Yes,
these.
yeah, these are easy. Like we have to just separate in the form of x, 10x and 10 square x. But here we can apply the integration by parts, and we can separate the power as well. So you have two options here. Okay, let's do this example number 9, and then we shift ourselves to the trigonometric substitution. So this question is sine 4x cos 5x dx. Did you get the last video link? I'm on the YouTube. Have I sent you?
I didn't receive the link.
Okay, I will send. I'll be sending you today. Actually, forgot it.
Okay.
Okay, there is a formula. Again, three formulas. So where you have double angles here, sine A cos B, sine A sine B, and cos A cos B. So you can apply these formulas to evaluate your functions. So we have sine and cos. So we can apply this formula, the first one, which is half sine A minus B plus sine A plus B. So how will you applying this? Half sine A minus B and plus sine A plus B. So this is my A and this is my B. So it will become half sine A minus B is A minus B is minus x. 4x minus 5x will become minus x plus 4x plus 5x will become 9x. Is it clear?
Yes.
Okay, and then this is very easy for me to do it. It is sine x, sine minus x plus sine 9x dx. The integral of sine x is actually an odd function. the cos x, cos minus x is an even function. So whatever is in the minus x, it becomes cos x. Again, the tan x is also an odd function. So sine minus x will become sine x, minus sine x plus sine 9x dx. So it becomes half. Sine x will become cos x, and minus sine x is actually minus cos x, and minus minus becomes plus. So I just wrote cos x minus sine 9x is cos x minus cos 9x divided by 9. And there's a plus plus of integral. This is the answer. Is it clear?
Yes.
Okay. Now there's an exercise questions. Okay, now we have our next topic, which is trigonometric substitution. These three formulas, we just need to remember this. We have already used these identities before, but these formulas are new to us. So if our expression is in this form, we can substitute these x to solve our question. So our first example one is evaluates 9 minus x square over x square dx. Our function is 9 minus x square. Okay, let's see which expression is we can apply, which substitution we can apply. 9 minus x square. Can we apply this expression? Because this is in plus form, so we can't apply this. This is here x square is positive, so we can't apply this. So the only option is that we should apply x square minus a square. Our 9 minus x square is similar to what this is. Now we have to identify what is our 3. What is our a? It's similar to a square minus x square. Now can I write 9 in this form? 3 square minus x square. So my a is 9 here. My a is 3 here. And now I have to see what is the substitution here. Substitution is here. Here is x is equals to a sine theta. So x equals to a is 3 sine theta. This is the substitution that I can place here instead of x. Now I need to find out what is dx here. So dx is equals to 3. The derivative of sine x is cos x, cos theta, d theta. So let's substitute these things inside this function. Square root 9 minus, instead of x square, I can write down 9 sine square x. And again, instead of x square, I can write down 9 sine square x. And instead of dx, I can write down 3 cosine x d theta. So
Can you repeat please how we found dx is equal to 3?
Okay, I differentiated this function, which was x equals to.
Okay.
Yeah, so it becomes 3 cos theta d theta. So can I take 9 common from the numerator? And we know that 1 minus sine square theta is equals to cos square theta. I'm sorry, here is x only. Then it's not x anymore. It's in terms of theta now. So it is 3 cos theta d theta. So taking 9, the square root of 9, it becomes 3. And instead of 1 minus sine square theta, I can write down 1 cos square theta over 9 sine square theta multiplied with 3 cos theta d theta. This 3 becomes 9. 9 divided by 9 cancel out. And square root of cos square theta is cos theta divided by sine square theta and cos theta d theta. I mean, this is only cos here because cos d theta. So it will become cos square theta sine square theta d theta. And we know that cos over sine is equals to cot theta, and there's a square, so it becomes cot square theta d theta. There is an again identity, that is 1 plus cot square theta is equals to cosec square theta. So cot square theta will be cosec square theta minus 1. And now we have to find out what is the integral of cosec square theta. Which is minus cos theta. You know why I use the identity that cot square theta is cosec square theta minus 1, because there in the formula sheet there isn't any direct integration is listed here. The direct integral of cot square x is not listed here.
Yeah, I just wanted to ask that.
Yes, so cosec square x is there, but cot square x is not there. So it's easier for us to use now that identity. So cosec square x, the integral of cosec square x is minus cot theta, and the integral of minus 1 is x plus c. I mean minus theta, not minus x. This is the answer. Is it clear?
Yes.
Okay, it's all about remembering the identities. Our target is to convert from x to theta form, that in the trigonometric identities. When I was integrating it, it was completely in the form of theta. It was completely in the form of cos, sine, cosec in terms of theta, not in terms of x. So we have to convert our function completely into the theta form, then we can integrate it. Let's leave this example number 2 for now. Okay, now let's do example number 3, which is 1 over x square plus 4 dx. In example number 3, we'll be doing the same thing. Like we have to first identify which substitution we will be using, and then we have to convert everything in the form of x, which is in the form of x, we have to convert in the form of theta. So it is 1 over x square plus 4 dx. Okay, now let's get back to the question, chart. We have x squared plus 4. So we need a substitution which has plus. So we can apply this substitution, which is a square plus x square, and which is equals to x equals to a tan theta. So I can write it down like this: x square and x square plus 2 square. Here my a is 2 and my substitution is x is equals to a tan theta. So it will be x equals to 2 tan theta. Now I have got x. I can replace it with, now I have to replace dx. For that I have to differentiate the function 2 as it is. The derivative of tan theta is sec square theta d theta. Now I have x and dx. I can replace this in this function. So it becomes 1 over x square is 4 tan square theta x square is 4 tan square theta plus 4. Okay, and dx is 2 multiplied with sec square theta d theta. 1 over 4 tan square theta. Can I take 4 common? And it becomes tan square theta plus 1. And here it is 2 sec square theta d theta. Square root of 4 is 2. And 2 multiplied with 4 becomes 8. Tan square theta. And we know that 1 plus tan square theta is sec square theta. And 2 sec square theta d theta. Okay, and the derivative in the square root of sec square theta is sec theta. And 2 sec square theta d theta. This sec theta is cancelled out with this sec theta. And 2 goes into it by 4 times. So it becomes 1 over 4 sec theta over tan square theta. And again, yes, we have to take its integral. This is d theta is here. If I can apply here U substitution. If I take U is equals to sec theta, then my derivative of sec theta is gonna be sec square theta. I mean, take tan square theta.
Why here don't we take U as tan?
That's what I was trying to do it now, because the derivative of sec is sec x and tan x. So sec x is there, but tan x is not there. So it's not useful to use u as sec theta. If I take u as tan theta, then my du is gonna be sec square theta d theta. Again, I don't have any square of sec square theta. I have only one sec theta. So even if I can replace sec theta d theta with du, it's not useful to apply u substitution here. Now we have to again apply the identities to convert it into the simpler function where we can apply the u substitution. Now we know that sec theta is equals to 1 over cos theta, and our tan square theta is equals to sine square theta plus over cos square theta, and there's d theta. 1 over 4, 1 over cos theta, reversing the function, so it becomes cos square theta over sine square theta d theta. So it becomes 1 over 4 cos theta over sine square theta d theta. Now I think the function is in the form of sine and cosine. I can apply the u substitution here, taking u as sine theta. My du will be cos theta d theta. Now I have cos theta d theta there in the function. So it becomes 1 over 4 du over sine square theta will become u square theta. So it becomes the integral of u square will become, adding power to it, so it becomes -1 divided by -1. It becomes 1 over 4 u, and my u is equals to sine theta. So 1 over sine theta is equals to cosec theta. There will be, of course, a plus integrals constant. So this is the answer. Is it clear?
Yes.
It is more, it requires a lot of practice, which identity we should use and which identity we should not use. And I think this method is easier than integration by parts.
Yes.
Because we just have to memorize the identities here. Okay, let's end it here. And in the next sessions, we are going to continue with the more questions on the examples questions on the trigonometric substitution. And if you have any question like from the exercises that you can ask me, we can solve it too.
Okay.
Okay.
So when will be the next session?
Today is Friday. Yeah, we can do it tomorrow. Even if I'm free on the Sunday as well.
I think tomorrow I will be busy because I have physics midterm tomorrow, and I think I'll be busy.
So okay, we can do it on Sunday then.
Okay.
Okay,
I will confirm about the WhatsApp. Okay.
Okay. Yeah. Sure.
Thank you so much.
Thank you. Bye.
Bye.